Hello everybody. In this video I'm going to show you how to write out all the resonance structures for benzene. In this case we're being given the formula, but we're also just being given the skeletal structure right off the bat. They think we wouldn't have pieced together that we needed to double that around and make a ring like that. We still need to figure out how many valence electrons we have so that we can figure out where can we place double bonds and lone pairs here and where would they belong. So we're going to start off by saying that we have carbon and we have hydrogen. Carbon gives us 4 valence electrons. Every hydrogen's giving us 1 valence electron. That means that in our bank we have 6 times 4 electrons plus 6 times 1 electron. 24 plus 6 is 30 electrons. Let's see how many bonds we already have. We have 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds and 1, 2, 3, 4, 5, 6 carbon-carbon bonds, so that's a total of 12 bonds from our bank. 30 electrons minus 12 bonds worth of electrons is 30 minus 24. We have 6 remaining electrons to place, and we need to decide where those electrons should go. So if we look at this, all the hydrogens are already happy. They all have their 1 bond. They're good. If we look at it from carbon's perspective, 1, 2, 3, 4, 5, 6. If I placed a double bond or a lone pair on this guy, he's now going to be happy, right? The problem with that is by the time I try to put a lone pair on them, I only get halfway around before I run out of valence electrons, right? I had 6 dots to place. This carbon's happy now, this one's happy, this one's happy. They all have their full octet, but these 3 don't. That means that we need to start sharing these lone pairs amongst them. We need to make bonds between these carbons. So let's try that. So if I make a bond here, now this carbon has 1, 2, 3, 4, 5, 6, 7, 8. This guy has 1, 2, 3, 4, 5, 6, 7, 8. Both of these two are now happy. We can go to the next one here. He needs a bond too. And then these two are both happy, right? They both have 1, 2, 3, 4, 5, 6, 7, 8, 5, 6, 7, 8. And then we could make another bond right there. And now everybody's happy. They all have their octet, and we've exhausted our 6 electrons. And the question is, how is this a resonance structure? Well, the answer is we could have drawn all of these bonds alternating the other way. Okay, so we could have just as easily have drawn this like this. Instead of having a double bond here, we would have a double bond here, we would have a double bond here, we would have a double bond here, single, 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 with all of our hydrogens. And I actually find this pretty interesting. This kind of implies that these double bonds can just kind of continually move around this circle here. And if you know anything about physics, that would be electrons moving in a circle, constantly accelerating, constantly changing directions, which would mean that it should induce a magnetic field. And in fact, we've actually been able to measure the magnetic field of these molecules and prove that this is true, that there's actually something called ring current, where these electrons are moving in a circle all the way around there. But these are our two resonance hybrids. You're going to see this structure appears a lot in nature and in organic chemistry. You're rarely going to see somebody draw out something like a resonance hybrid for this with all of the carbons and hydrogens explicitly done up like this. This is just kind of a thing that we do in the beginning courses. Often what you're going to see is this actually condensed down to something that looks like this, just a hexagon with these double bonds indicated there. And I've even seen people get pretty lazy with this and do something like that, just to indicate that there's a circle of double bonds there. This is part of a class of organic compounds called aromatics, kind of a historical name because they smell. And in fact, benzene, even though it's wildly carcinogenic, is a big component of that smell you smell at gas stations on a hot summer's day.